Good afternoon, everyone. Welcome to Compass Wednesday. Today, our speaker will be Kelsey Malloy. Kelsey is a fifth-year PhD candidate in the atmospheric department. She received her Bachelor of Science in Atmospheric and Oceanic Science from University of Maryland in 2017. Her advisor is Dr. Benjamin Kurtman, and her research interests include climate variability and climate dynamics. Outside of her research, she really enjoys yoga and outdoor activities like hiking, snorkeling, and canoeing. Today, Kelsey will talk about the Asia-North America teleconnection and its modulation by ENSO, which can describe summer rainfall variability over the United States. Kelsey, the stage is yours.
Thanks, Basin. Okay. Good afternoon, everyone, and welcome to Compass Seminar. Today, I'll be talking about some recent work that I've been doing with Ben Kurtman on understanding the summer Asia-North America teleconnection and its modulation by ENSO. This is not a very well-known teleconnection. I'm sure many of you have never even heard of the ANA teleconnection. So today we're going to spend some time to dive into it a little bit and explore it using 3 different models of varying complexity. And so this will help us understand rainfall variability over the United States. Okay, so let's begin with some motivation. There are regions of the US, like the West Coast and Plains Midwest regions, that are particularly vulnerable to flooding and drought disasters. So these would be the extremes of rainfall. What you'll see here is the United States billion-dollar disaster types separated by month. So here on the x-axis are months, so January through December. And you can see 2 different types. I filtered out 2 different types of disasters. So the mustard color is drought and blue are the flooding types. You'll see that many of the events occur during the warm season. And I'm particularly interested in the summer season because this is important for agriculture, especially in regions like the West Coast, like California, as well as the Plains Midwest regions. But we can also think of this in terms of cost per year. So this is billion-dollar drought and flooding disaster costs per year separated by state. And you can see that there are relatively higher costs occurring in the center of the US, so the Plains region, and California is also highlighted over here. In general, subseasonal to seasonal prediction of precipitation is limited, especially in the summer months. In the winter, we have a relatively fast jet stream. It's lower in latitude. And then we have features like the El Nino Southern Oscillation and the Madden-Julian Oscillation that are very active, and the anomalies associated with them are a lot stronger in this season. So that means that they can disrupt the jet stream and cause these Rossby wave responses that make its way to the United States. However, in the summer months, we have a jet stream that moves further north in latitude. It's weaker, and our features like ENSO and the MJO are weaker. In fact, the MJO does not propagate as far into the Pacific during the summer and rather becomes a part of this entire monsoon circulation. So as you can see here, this is the boreal intraseasonal oscillation. This is a mode of variability that describes a northeastward propagating signal of wet and dry signals. In general, in the summer, high impact events are associated with quasi-stationary Rossby waves. These are circumglobal teleconnections, so circulation patterns that reach across the globe that are usually active because of monsoon activity. This has contributed to forecasts of opportunity. So these are times when we can be more confident in certain S2S forecasts, or these events are more persistent, so we can condition the scale such that we have relatively higher scale in these forecasts when we have these features present. These Quasi-stationary Rossby waves are also associated with coupled processes. So that means that they're associated with slowly evolving parts of the Earth system, like the ocean or the land. And this helps amplify or sustain these planetary waves. In general, circulation is better forecasted on the S2S timescale than variables like 2-meter temperature, or in this case, rainfall. So it's beneficial to understand circulation for S2S predictability. We demonstrated this in Malloy and Kurtman 2020 by trying to understand the forecast of opportunity associated with Great Plains low-level jet events and their associated precipitation. So you'll see here that there are 4 predictors associated with a shift in distribution towards stronger Great Plains low-level jets and increased precipitation. However, the greatest shift is seen with the combined influence of the circulation predictors. So when a strengthened Caribbean low-level jet and a negative PNA is present simultaneously, this can be used as a forecast of opportunity for predicting precipitation in the plains associated with these Great Plains low-level jets. So I talked a little bit about the monsoon circulation. So on the intraseasonal timescale, we have this northeastward propagation of wet-dry signals. But we can also think of the entire Asia summer monsoon as having these 3 branches. So the Indian summer monsoon, the West-North Pacific summer monsoon, and the East Asian monsoon. And on the seasonal to interannual timescale, one of these branches can be more active or stronger than the other branches. And I'm particularly interested in the East Asian monsoon because this is higher in latitude than the other systems, and therefore it has the greatest opportunity per se to interact with the East Asian jet and trigger Rossby wave responses, which contribute to teleconnections throughout the globe. There's been a documented connection between East Asian rainfall and US rainfall, and we call this the Asia-North America teleconnection. I really want to focus on Zhu and Lee 2016 paper. They were able to force the atmosphere with heating, and I know it's hard to see these borders in light gray, but this is the East Asia region right here, and they were able to produce a Rossby wave response that makes its way to North America over here. They were able to associate the ANA teleconnection with the first mode of rainfall variability over the United States. However, at the same time, ENSO has its own effect over the North Pacific. So we can think of this in 2 ways. First, ENSO can directly influence US hydroclimate because the anomalies in the tropical Pacific can influence rainfall anomalies in the tropics, which then can affect the Rossby wave response that makes its way to the United States. So this is usually what we think about when we talk about the ENSO to PNA connection. However, ENSO can indirectly influence US hydroclimate, and that's via understanding how ENSO influences monsoon variability. So even if we don't think about the wave train pattern, we have these rainfall anomalies that makes its way to, or affects, I should say, the Indian Ocean as well as the far West Pacific, which can affect that monsoon circulation that I had talked about in the slides earlier. So overall, ENSO can both directly and indirectly modulate CONUS hydroclimate. And so we're going to talk about both those types of modulation throughout this talk. So the main goal of this seminar is to dive into that teleconnection deeper. First, does the ANA teleconnection exist in observations? And how does a state-of-the-art model like CAM5 simulate this teleconnection? With CAM5, we can test whether SST variability like if ENSO, how that modulates the ANA pattern. We can also explore the teleconnection in simpler models. So how can we look into the processes in a more simple way to understand this pattern? And with that, we can try to explain some of the biases we see in CAM5, some of the differences between our CAM5 experiments, and how can we explain both indirect and direct ENSO modulation with simple models. CAM5 is the atmospheric component of NCAR's CESM. In this model, the ocean is not actively evolving, but it is prescribed ocean data. So what that means is that the ocean can influence the atmosphere, but the atmosphere can't influence the ocean. I'll be looking at 30-year simulations and only looking into the summer JJA monthly output. So we ran two main experiments that I'll be talking about today. The first is global prescription of climatological SSTs, and the second, we prescribe observed SSTs. The main difference between these two experiments is that with the observed SSTs prescribed, we have this variability in the global SST anomalies that you see there. However, in the experiment with the climatological SSTs, we are filtering out that variability because we're taking the time mean of it. So that's the main difference that you should hold in the back of your head when we talk about the difference between the experiment with climatological SSTs and with observed SSTs prescribed. And with that, we'll start with part one. We're going to dive into what the ANA teleconnection even looks like in observations and how CAM5 simulates it. Okay, so first we're going to look at composites. So what you see here is a composite of precipitation anomalies, first averaged during strong monsoon events, and then subtracted by the average precipitation anomalies during weak monsoon events. So over here in East Asia, we have this nice monsoon-like circulation of dry, wet, dry anomalies in a meridional structure. And the East Asian monsoon is associated with this wet band of anomalies around 30 degrees north. We also see statistically significant anomalies over the United States, particularly over the West Coast in that purple box, and over the Plains Midwest region in that pink box. Now, if we think back to that Zhu and Lee 2016 paper, we can see that we are able to reproduce that general northwest-southeast dipole in rainfall patterns. So we're able to reproduce that from that paper. But we can also think about this in terms of distribution. So what we can do is that we can take for every month and for every grid point within the box, so again, West Coast and Plains Midwest, we can take the precipitation anomalies associated with a strong monsoon, so that's in red, and compare them to the anomalies associated with a weak monsoon in blue. And you'll see that during a strong monsoon, we shift the distribution to the right. So that means it's associated with higher probabilities of wet anomalies. And so we can compare that to first our experiment with the climatological SSTs prescribed. And what you'll see is that over East Asia, we have a similar monsoon circulation, not perfect, but it's represented. Over the US, we have the similar signal over the West Coast, so a wet signal like in observations. However, over the Plains Midwest region, we see more of a dry signal. So this is not like what we see in observations. And you can see that in the distributions, similar results that verify this. And then finally, in the experiment with the observed SSTs prescribed, we can see that the circulation is present over East Asia, and over the United States, however, we can see that over the West Coast, we don't have the same anomaly signal, but over the Plains Midwest region, we see the same signal as with observed. So we see this wet pattern. However, we also want to take a look at what the circulation is is related to the monsoon. So what you see here is still composite, but now we're looking at 250 millibar height, and this asterisk means that we're only looking at the zonally asymmetric component. So what that means is that we're looking basically at stationary wave composites associated with the monsoon. So in observations over East Asia, we get this general meridional pattern that we see over East Asia. Over North Pacific, we have this elongated ridge. And then over North America, we see a general pattern of kind of this southwest, northeast dipole structure present. And so keep note of what this pattern looks like, because we'll be talking about it a lot. And then we can compare it again with the CAM5 experiments. And really what I want to focus on is what's going on over North America. So in the CAM5 experiment with climatological SSTs prescribed, we see a much different pattern over North America compared to observations. So we actually get the opposite pattern. However, in the CAM5 experiment with observed SSTs prescribed, we see that we get a better or improved representation of the ANA pattern that looks a lot like observations. So overall, we're able to kind of find this relationship between the monsoon and rainfall variabilities over the US. And the ANA teleconnection is improved in our experiment with the observed SSTs prescribed. So maybe your next question is, if it's better represented in the experiment with SST variability, is that because there's an ENSO cycle? So does ENSO matter when we think about the ANA pattern? And so we're going to dig into that a little bit further by separating these patterns by ENSO phase. So we're going to look at the same type of composites, but now our rows are going to separate them into ENSO phase. So I began with just looking at the neutral phase, which looks a lot like our patterns when we didn't consider ENSO. And then we can compare it to our El Nino, so our composites taken during El Nino events, and our composites taken during La Nina events. And what I really want to highlight are the differences that are happening over North America. During El Nino, over the Plains Midwest region, we see enhanced precipitation signals over the region, whereas during La Nina, we actually see either no signal or even dry signals. If we look at the distribution, we actually see that during La Nina, a strong monsoon is associated with a higher probability of dry anomalies. And if we look at the stationary wave patterns, during La Nina, we actually get this reversal in the dipole pattern. So we have an opposite pattern than we see during neutral or during those events when not considering ENSO. So overall, ENSO seems to be really important for understanding the ANA pattern, particularly over CONUS. And then we can finally compare this to CAM5 with the observed SSTs prescribed. And again, I want to focus on North America for this talk. And you'll see that during El Nino, as well as the neutral phase, we're able to generally simulate the similar patterns over the Plains Midwest as with observed. But if we look at La Nina, we see these extremely strong wet anomalies. Now, this is not what we had seen in observations. I want to flip back so that you can see. And then we can also note that the distribution is in the opposite direction, or the shift is in an opposite direction. And our stationary wave pattern is unlike what we saw with observations as well. It's the opposite. So in our CAM5 experiment with the observed SSTs, even though the ANA pattern was improved, this is really limited by what's happening during La Nina in this CAM5 experiment. So in this part one, I want to give a short summary of what we've seen so far. We saw that ANA patterns were different between observations and the CAM5 experiment with climatological SSTs. We saw that patterns were different between our two CAM5 experiments, so with prescribed climatological SSTs versus observed SSTs. we saw that ENSO greatly modulates the ANA patterns over CONUS, but the ENSO-modulated patterns in CAM5 with the observed SSTs were a lot different during the La Nina phase. So we've seen a lot of biases and we've seen a lot of differences. And so the next part is to try to understand maybe what the relative role of the mean state and the forcing is in producing these differences and biases that we see between the observations in CAM5 and between the CAM5 experiments. So with that, I'm going to move into part 2, which is going to talk about the roles of the mean state and forcing. Okay, so this next model is based on linear QG dynamics. So we're going to go back to our atmospheric dynamics class and start with the linear QG vorticity equation. So we have this equation that's broken into these terms: geostrophic vorticity advection by the geostrophic zonal wind, and the advection of planetary vorticity by the geostrophic meridional wind. These two terms on the left compete to balance out the divergence forcing on the right-hand side. And so we actually know some of these variables that we can plug in. The divergence forcing, or F, can come from the East Asia monsoon-related divergence forcing, and our U bar, or a mean state, is just the climatology. So we're going to take that to be the 250 millibar zonal wind, or the jet stream. We can plug in these variables, rearrange our equation, and solve for our VG. And then when we solve for a VG, lastly, we just want to turn it into a geopotential height field instead, just so that we can better compare to our original composite patterns. So I think it's best to try to explain this further just by jumping into it. So we're going to jump into the linear QG solutions. And what we're going to do is, again, plug in a U bar, or a mean state, and the F, or forcing. And we're going to start by plugging this in from observations. So we're going to take our 250 millibar zonal wind climatology from observations and plug it in as U bar. And we're going to take a strong minus weak monsoon divergence anomaly composite and plug that in as our F from observations. And you'll see that in this plot as the light gray for mean state, and our forcing is the green and the purple contours. And when we plug this into the equation, we can solve for our geopotential height, which is what you see there in the red and blue shaded contours. And so what I want to do is compare that to our original composite. And we see some similarities. Over East Asia, we're able to simulate this meridional structure in the height field. We're also able to simulate over North America a very general west-east trough ridge-like pattern. However, we lose a lot of the details over North Pacific. So the linear QG model is not able to simulate that elongated ridge, for example. So next, we're going to plug in the U bar and F, but this time from our respective CAM5 experiments. So let's start by plugging in U bar and F from the CAM5 experiment with prescribed climatological SSTs. And again, we're going to compare this to the composites. And again, we see a lot of similarities. So we have a more zonal wave pattern. We can also see over North America that we have in general the same pattern, and that this pattern is opposite to what we had seen in observations. And then somewhat surprisingly, when we plug in the U bar and F from the experiment with observed SSTs, it looks the same as the top panel, as you can see here. What we can do next is try to understand the biases by taking the correct F and plugging it in. So what we're doing is taking the F from observations. So you'll see that the purple and the green are the same as the top panel, but we're going to keep the mean state to be from the different CAM5 experiments. So what we can get from this column is that how close do we get to this top panel? So how close can we get to the correct response? And if we see differences between these two panels, we know that we can attribute those differences to differences in the mean state between the two experiments. So first, we notice that we improve the representation of the response over East Asia, and we get closer to the response. So this over North America is closer to our top panel when we have the correct forcing. And then maybe subtly, we see some differences over the North Pacific. So maybe there are, differences over the North Pacific responses that can be attributed to the different mean states in these CAM5 experiments. And then we can do the opposite. So now we're going to take the mean state from observations, and we're going to keep the different Fs from our experiments here. And so same idea, we're going to first see if we get any closer to this top panel, and we actually don't. So we don't change too much. So that means that mean state is not really explaining the biases we see in the ANA pattern. And we also see that these two panels are very much the same. So overall, the forcing is really, really important for studying the structure of the monsoon response. So that means that forcing, the biases in the forcing in CAM5 are greatly contributing to the biases in the ANA pattern. And so we can see how different the forcing is just by looking at the purple and green contours in these panels, and see that those biases are contributing to the biases in the ANA. Also, mean state was maybe less important for the ANA pattern biases, but maybe it contributes to the differences that we see between our CAM5 experiments, though very subtly. Next, we can look into ENSO's indirect modulation. So there are two ways that ENSO can modulate the ANA pattern indirectly, and that's through the forcing or the mean state. So what we're going to do is condition the F or the U bar on ENSO phase. So that means we're only going to take F or U bar during El Nino or La Nina, and then compare those responses. So what you'll see here is that we're going to separate the rows by ENSO phase. So we'll start with conditioning by El Nino. And then each of our columns are going to be either observations or in our CAM5 experiment. So again, we're taking F to be the strong minus weak divergence anomalies, but only during El Nino in observations. And then we're keeping U bar to be the same as before. And same idea in the CAM5 experiment. So what you'll notice first is that, again, CAM5 is not simulating the same thing as we see in observations. So again, this just reiterates the fact that forcing is really important to get correct if you want to simulate the ANA pattern. Next, we can compare this to the conditioned F on La Nina. And if we look at the two rows, we can see that there's not really much of a difference. So overall, conditioning F on ENSO does not seem to explain the ENSO-related ANA pattern differences. And again, as a mini summary, again, F is really important for studying the structure of the response. And then we're going to condition now mean state on ENSO. So that means that we're going to take our jet stream climatology only during El Nino, and the same as this previous slide in observations versus CAM5 experiment. So the first thing you'll see is that during El Nino, we get a much enhanced response over the North Pacific. And if we compare this to CAM5, CAM5 is actually gets some of this structure more correct over the North Pacific. So it's able to at least somewhat be similar to the observations. And then we can compare this to conditioned on La Nina. And first, if we want to compare the rows, we can see that conditioning the mean state on ENSO does seem to produce different ANA patterns. So that's number one. And then two, we can see that CAM5 is unlike the observations during La Nina when we condition it on the mean state. So overall, conditioning the mean state on ENSO does help to explain those ENSO-related ANA pattern differences. And maybe we're able to understand why during La Nina and CAM5, we see much larger biases than we do for El Nino in particular. So in the second part, we found that the linear QG model was able to describe the relative importance of the forcing and the mean state. We found that F is really important for the ANA pattern. So the biases in the forcing in CAM5 are greatly contributing to its biases in the ANA pattern. We also saw that mean state is important for understanding ENSO's modulation, indirect modulation on the ANA pattern. And then CAM5's Niña-related biases were highlighted by conditioning mean state on ENSO. However, we weren't able to simulate the subtropical response or any of those details. We aren't able to assess any variability or the robustness of that steady state pattern using the linear QG model. We weren't really able to describe the differences that we had seen between our two CAM5 experiments. It was not clear. And then we haven't talked about ENSO's direct modulation. So it has its own forcing in the tropical Pacific, and so its own patterns that can interact with the patterns from the East Asia monsoon heating. And so with that, we're going to introduce a nonlinear dry model to try to understand and fill in these gaps. And with that, we can move into part 3. So this model is a simple dry model. That means that there's no moisture or precipitation in this. It is a fairly coarse model, though it does have 26 vertical levels. And what we input into the model are two things. First, a mean state. So we're going to input JJA surface temperature climatology. And then we also input a heating forcing. So that part is optional. And then we run our experiments out 900 days, excluding the first 100 days of spin up. The first set of experiments that I'll be talking about are just our monsoon forced experiments. So what that means is that we just force heating in the East Asia region. And that means ENSO is not included because we're not forcing heating in the tropical Pacific. And because our mean state is a climatology, it does not have any SST variability. And so we're going to get 3 different responses. And the way we calculate those responses is that we run experiments in a respective mean state. And we take an experiment with monsoon forcing, take its long-term mean, and subtract it from the experiment with no monsoon forcing. And we're able to calculate a response. We're also able to calculate the robustness of that long-term time mean response. And we can do that by taking the standard deviation of the 90-day delta Z250 moving mean. And what that means is that we have a time series of the difference between the 250 millibar height. And so at every grid point, we have that time series of the difference. We can take a 90-day moving mean and then take the standard deviation of that. And in that way, we can standardize our long-term responses to see if they're statistically significant or robust. And in general, just to see, so if we input our observations, for example, we can see that our variability is greater in the mid to high latitudes, probably not surprisingly. So let's take a look at these responses. So again, we're going to first show our dry nonlinear response when we input observations as the mean state. And we're going to, again, compare it to our original composite pattern. And we can see that we simulate a lot of the same features. So over East Asia, we have this general meridional pattern. We now have this elongated ridge being simulated, as well as the trough above it. And then generally over North America, we have this southwest northeast dipole in the height field. So in general, we're able to simulate many of the patterns in this nonlinear model. And so we can do the same thing by inputting our respective CAM5 runs. And again, compare that to the original composites. And you'll see that over the North Pacific, the nonlinear model is able to capture a lot of the same pattern. So it's a lot zonally oriented. And we can see that that is different from the original one with the observations input. However, we're not able to simulate a lot of the differences over North America. And then finally, just to show you that we could also look at the upper level divergence. So because we don't have precipitation or moisture in this model, what we can do is instead look at upper level divergence to understand large scale precipitation patterns. And what we get when we heat the monsoon forcing, or we have a forcing of monsoon heating, we generally can simulate West Coast precipitation as well as plains, very generally. And these are, in general, very weak. So I'm not going to really show these response results. I'm going to focus on the circulation field for the rest of the talk. Overall, it seems that this nonlinear model explains a lot of the observed ANA pattern, especially over the subtropics now. And however, for CAM5, it's only able to simulate the North Pacific pattern. So finally, we're going to look into direct ENSO modulation. So what we're going to do is look at the Niño and Niña-modulated experiments. So what this means is that this set of experiments heats East Asia region as well as the tropical Pacific associated with ENSO. And so in this set of experiments, ENSO is included, but we're going to calculate the part of the response a little bit differently than before. So now we're going to have an experiment with both heating and subtract it from the experiment with only monsoon heating. So essentially what we're doing is extracting only the Niño or Niña modulated part of the response. So it will be interpreted a little bit differently than before. So what we're going to do is first look at the Niño modulated part of the response. And what we're going to do is compare it to our original pattern that didn't have ENSO. And you can see that we have these negative anomalies that are opposite to our original pattern. So what that means is that Niño modulation is destructively interfering with our original monsoon forced pattern. We also see over the United States that we have the same sign over Western North America. So that means that Niño modulation is constructively interfering with our original pattern with just the monsoon forcing. And then we can compare this to our original composites that were separated by ENSO phase. So if we compare it to our observed Niño-related ANA pattern, we can see that we simulate Niño modulation where over North America, we have a general ridge, trough ridge-like pattern. So in general, we're able to understand Niño modulation. And in general, in this model, it destructively interferes with the ANA pattern over the subtropical Pacific and constructively interferes with the pattern over CONUS. And then finally, we can look at what happens when we input CAM5 into the model. And Niño modulation is the same over subtropical Pacific, but it's very different over North America. So again, we want to compare this to the Niño-related ANA in CAM5. And we can see that maybe overall, there are some parts of the pattern that are similar. So off the coast, we have this trough, we have this curve in the ridge-like structure, and negative anomalies above it. But I will point out that this pattern over here is not statistically significant, so it's difficult to conclude anything. Overall, though, there is some agreement with Niña modulation when we input CAM5 as mean state. And then finally, we're going to look at Niña modulation. So this is the Niña modulated part of the response that we want to compare again with our original pattern with only monsoon forcing. And we can see that over the tropical and subtropical Pacific, we have constructive interference that we can see from the same sign. So Niña modulation constructively interferes with the pattern over subtropical and tropical Pacific. And again, we can compare this to our Niña-related ANA composite patterns. And again, what you'll see here is that we have this destructive interference with the original pattern over the Western North America, which correlates well with what's going on in those Niña-related ANA patterns. So we're able to simulate general patterns of Niña modulation on the ANA pattern. All in all, Niña modulation constructively interferes with the ANA pattern over the subtropical Pacific, but destructively interferes with a pattern over CONUS. So overall, this is explaining why during La Niña, we get decreased signals, precipitation signals over the plains Midwest, for example, because we have this destructive interference with the ANA pattern. Finally, we can see if the same thing happens when we input CAM5 as the mean state. And we have similar results in the tropical and subtropical Pacific, as well as over North America, the same constructive and destructive interference. However, if we compare this to our CAM5's Niña-related ANA pattern, we see some discrepancies. So I want to point out that the forcing in this model is the same, whereas we know that CAM5 has biases in the forcing. It should be maybe in a different location. So maybe that's contributing to the discrepancies that we see between these two plots. But overall, there seems to be little agreement with Niña modulation when we input CAM5 as the mean state. And with that, we are going to wrap up with an overall summary. Hopefully, I was able to convince you that there is a relationship between the East Asia monsoon and CONUS rainfall, and we call that the ANA teleconnection. ENSO greatly modulates the ANA pattern, especially over CONUS. So it's important to understand how ENSO phases change that ANA pattern. We also saw that there was improved representation of the ANA pattern in our CAM5 experiment with prescribed global SST variability. However, this was really limited by ENSO phase. So during La Niña, there were greater biases in over North America than during El Nino, for example. In our second part, we saw that the linear QJ model was able to explain some of these differences in biases by understanding the roles of mean state and forcing. Biases in the forcing in CAM5 greatly contributed to the biases in the ANA pattern. Indirect ENSO modulation via mean state differences is really important for understanding the ENSO modulated ANA response. And then biases in the ENSO-related mean state in CAM5 at least partly contributes to why there were such big discrepancies during those La Niña phases. And then finally, with our dry nonlinear model, we're able to explain some details of that ANA pattern well. For example, that subtropical Pacific response was improved with the nonlinear model. We were also able to directly apply ENSO forcing, which was helped simulate the CONUS pattern. And so we were able to simulate that during El Nino, the El Nino modulation constructively interferes with the ANA pattern over CONUS. And so that explains why we see enhanced precipitation signals during the El Nino months versus La Niña, which destructively interfered with the ANA pattern over CONUS. and had reduced precipitation signals. However, I want to take the time to talk about some limitations. So there are other sources of global SST variability that could be important for simulating hydroclimate, as well as understanding even ANA modulation. So for example, North Atlantic SST variability is important for US hydroclimate and could be important for how CAM5, for example, simulates the ANA pattern over CONUS. And neither of our simple models had land moisture feedbacks. And so this is important for the maintenance of quasi-stationary Rossby waves. And so this could be important for understanding CONUS hydroclimate as well as the ANA pattern. And with that, I'll take any questions. Yeah, I think I am ready.
All right, thank you, Kelsey, for such a wonderful talk. For our audience, if you have any questions for our speaker, Kelsey, please unmute yourself, turn on your webcam, and launch questions. Or if your internet connection is bad, you can type that out in the chat section and I can read it out for you. Actually, I can see that we have a question here from Rossby Lopez. She says, great talk. How did you choose the amplitudes and vertical profiles of heating anomalies for ENSO and the monsoon? Was the ENSO heating different from that of the monsoon?
Yeah, great question. I chose the amplitude and vertical profile of the heating based on the Zhu and Lee 2016 paper. So that was 2 Kelvin per day, and it is centered at 300 millibars. I've tested different amplitudes, so instead of 2 Kelvin per day, 1 and then 4 Kelvin per day. And it does change the robustness of those responses, probably not surprisingly, but we feel that 2 Kelvin per day based on previous literature is appropriate. And the second part of that question, is ENSO different from the monsoon? In general, I tested different amplitudes. So if El Nino was 2 times, for example, the amplitude of the monsoon. But again, it really only changed the robustness. Maybe some of the patterns in the mid-latitudes as well were different. But again, when I looked at the divergence anomalies, they're on the same order of magnitude. They were around the same values. So I thought that would mean that they would have a similar heating anomalies associated with them. Hopefully that answers your question.
Any more questions for our speaker?
Thanks, Caleb.
All right, if there's no, I'm sorry, did I interrupt something?
No, that was just me.
Oh, okay. Well, I guess we have no more questions for today. Thank you so much for coming, Kelsey. Wonderful talk. And please stay tuned for our next student seminar on this Friday. 3 students will be presenting their research for 15 minutes to the seminar. And if you missed some part of today's talk, feel free to tune in for our YouTube channel, which the recording will be posted. Thank you so much for coming and have a wonderful day.
Thank you, everyone.